Question 11 reads, complete the following table. This will require us to draw some Lewis structures, including any resonance structures, geometry, predict the shape of the molecule, predict whether the molecule is polar or not, and then indicate the strongest intermolecular forces between molecules. Drawing a Lewis structure, there's a couple of different rules we want to consider. Remember that the number of dots around an atom will equal the number of valence electrons. Remember too that most atoms need 8 electrons. An exception there would be hydrogen, which only needs 2, beryllium and boron, which just needs 6. And remember as well that electrons must be paired. Considering these 3 rules, we can then begin drawing our Lewis structures. First structure is SiHF3. Silicon is going to be a good candidate to be in the middle of this molecule because it has 4 valence electrons, allowing it to make 4 bonds. From this point, we can see that you can plug in a hydrogen on one side and plug in fluorines on the other sides. Here I have the correct number of valence electrons. All of my atoms have 8, the hydrogen has 2, and all of the electrons are paired. At this point I can predict the geometry. There's 4 things around the central atom, and the best way for 4 pairs of electrons, or 4 atoms, to get away from each other is to form a tetrahedral shape. Because all 4 of those things are atoms, the name of the shape and the name of the molecule is also tetrahedral. This molecule is definitely going to be polar. Fluorine is very, very electronegative, so on the fluorine side of this molecule, there'll be a large delta negative charge building up, whereas on the hydrogen side, there'll be a large delta positive building up. Because this molecule is polar, it's going to do dipole-dipole bonding with other molecules. Next up, we have the carbonate ion, CO3 with a -2 charge. Again, carbon's going to be a good candidate to be in the middle because it can form 4 bonds. We'll put 4 electrons around carbon and then begin adding in 3 oxygens. Oxygen has 6 valence electrons, so we'll draw 6 around each here. And then, because this ion has a -2 charge, I can add in 2 additional electrons. At this point, not all of my electrons are paired, and carbon and oxygen don't yet have 8 electrons around them, so I want to move that electron and that electron into a double bond. What that will do is give an ion that looks like this, that does satisfy all of my rules. However, there's a couple more things I need to do to clean up that drawing. Because I'm a little bit out of space, I'm going to bring it over to here. I can represent the bonds with single lines and represent the double bond with 2 lines. I also want to indicate that this thing is an ion, so I'll put it in brackets and give it a -2 charge. However, note that that double bond can actually move between different oxygens. It can move to here, or it can move to there. So to represent that resonance of the double bond, I really want to draw all 3 resonance structures. That, and also that. Those 3 resonance structures combined are the correct Lewis structure for the carbonate ion. Another way to represent it would be to show that carbon always forms a single bond with the oxygens, and that that double bond can move around. And this is maybe the easiest way to represent the resonance structure, that it's truly a blend of all of those structures. Moving back to the chart, there are 3 things around the central carbon. And the best way for 3 things to get away from each other is to form a trigonal planar shape. Same thing for the shape name because they're all atoms. This molecule is not polar, it's in fact an ion. Therefore, the strongest kind of intermolecular force, it will do ionic bonding.